Multivariate regression. In a multivariate linear regression, the numeric output R is assumed to be written as a linear function that is a weighted sum of several input variables, x1, x2, x3 until xd, and noise. Actually, in a statistical literature, this is called multiple regression. Statisticians use the term multivariate when there are multiple outputs. The multivariate linear model is R to the t equals to g of R to the t conditioning on W0, W1, and so on to WD. Then, after we take the g function, we plus epsilon. So to expand that, it will be W0 plus W1 times x1 to the t plus W2 times x to the t and so on plus WD times xd to the t plus epsilon. As in the univariate case, we assume epsilon to be normal with mean 0 and constant variance, and maximizing the likelihood is equivalent to minimizing the sum of squared errors. That is, the expectations of W0, W1, W2, and so on until WD, conditioning on x, is equals to 1/2 times the summations of summing for all index t to the following terms to the square. That is R to the t minus W0 minus W1 times x1 to the t minus W2 times x to the t and so on until last term minus WD times xd to the t. So taking the derivative with respect to the parameters Wj, j starting from 0, 1, 2, 3 until d, we get the normal equations. That is, the summations of R to the t summing for index t is equals to n times W0 plus W1 times the summations of x1 to the t summing for index t plus W2 times the summations of x2 to the t summing for index t and so on plus WD times the summations of xd to the t summing for index t. Okay, by the similar argument, we know the following formulas. The summations of x1 to the t times R to the t summing for index t is equals to W0 times the summations of x1 to the t summing for index t plus W1 times the summations of x1 to the t to the square summing for index t. Then plus W2 times the summations of x1 to the t times x2 to the t summing for index t and so on plus WD times the summations of x1 to the t times xd to the t summing for index t. So this is just what we apply every term with additional parameters x1 to the t to the original summations of R to the t summing for index t and so on. So the second line should be, the third line should be the summations of x2 to the t times R to the t summing for index t, which is equals to W0 times the summations of x2 to the t summing for index t plus W1 times the summations of x1 to the t times x2 to the t summing for index t plus W2 times the summations of x2 to the t to the square summing for index t and so on plus WD times the summations of x2 to the t times xd to the t summing for index t. And so on until the last line. There will be the summations of x to the t times d to the xd to the t times R to the t summing for index t, which is equals to W0 times the summations of xd to the t summing for index t plus W1 times the summations of xd to the t times x1 to the t summing for index t plus W2 times the summations of xd to the t times x2 to the t summing for index t and so on plus WD times the summations of xd to the t then to the square summing for index t. So from all these previously formulas, let us define the following vectors and a matrix. That x equals to, the first row is 1, x1, 1, x2, 1, and so on until xd to the 1. The second row is 1, x1 to the 2, x2 to the 2, and so on until xd to the 2. The last row is 1, x1 to the n, x2 to the n, and so on to xd to the n. Let us define this as the matrix X, and we define the vector W equals to W0, W1, and so on to WD to the transpose. And we define that the vector R equals to R to the 1, R to the 2, and so on to R to the n to the transpose. Then the normal equations can be written as x transpose times x times w is equals to x transpose times r. I mean, for all those previously formulas that we have listed before, it can be simplified as following. And we can solve for the parameters as w equals to x times transpose times x to the inverse times x transpose times r. This method is the same as we used for polynomial regression using one input. The two problems are the same if we define the variables as x1 equals to x, x2 equals to x squared, and so on to xk equals to x to the k. This also gives us a hint as to how we can do multivariate polynomial regression if necessary. This is in exercise 7, but unless d is small, in multivariate regression, we rarely use polynomials of any order higher than linear. Actually, using higher order terms of inputs as additional inputs is only one possibility. We can define any nonlinear function of the original inputs using basis functions. For example, we can define new inputs x2 equals to sine of x, x3 equals to exponential of x squared if we believe that such a transformation is useful. Then using a linear model in this new augmented space will correspond to a nonlinear model in the original space. The same calculation will still be valid. We need only replace x with the data matrix after the basis functions are applied, as we will see later on the various guises. For example, multilayer perceptrons, or support vector machines, or Gaussian processes. This type of generalizing the linear model is frequently used. One advantage of linear models is that after the regression, looking at the wj, j equals to 1 to 3 until d values, we can extract the knowledge. First, by looking at the signs of wj, we can see whether xj have a positive or negative effect on the output. Second, if all xj are in the same range, by looking at the absolute values of wj, we can get an idea about how important a feature is, rank the features in terms of their importances, and even remove the features whose wj are close to 0. When there are multiple outputs, this can equivalently be defined as a set of independent single-output regression problems. Notes: a good review text on linear algebra is Strun, published in 1988. Haveli 1987 is another excellent book that looks at matrix algebra from a statistical point of view. One inconvenience with multivariate data is that when the number of dimensions is large, one cannot do a visual analysis. There are methods proposed in the statistical literature for displaying multivariate data. A review is given in Rancher 1995. One possibility is to plot variables 2 by 2 as bivariate scatter plots. If the data is multivariate normal, then the plot of any two variables should be roughly linear, thus can be used as a visual test of a multivariate normality. Another possibility that we discuss in Chapter 6 is to project them to 1 or 2 dimensions and display there. Most work on pattern recognition is done assuming multivariate normal densities. Sometimes such a discriminant is even called the Bayes optimal classifier, but this is generally wrong. It is only optimal if the densities are indeed multivariate normal and if we have enough data to calculate the correct parameters from the data. Rancher 1995 discusses tests for assessing multivariate normality as well as tests for checking for equal covariance matrices. McLaughlin 1992 discusses classification with multivariate normals and compares linear and quadratic discriminants. One obvious restriction of multivariate normals is that it does not allow for data where some features are discrete. A variable with n possible values can be converted into n dummy 0,1 variables, but this increases dimensionality. One can do a dimensionality reduction in this n-dimensional space by a method explained in Chapter 6 and thereby not increase dimensionality. Parametric classification for such cases of mixed features is discussed in detail in McLaughlin 1992.